So now we're going to be beginning Unit 4. And as we start Unit 4, the first thing that you want to notice is it's going to be entirely on thermochemistry. More specifically, it's going to be on heat and heat energy. So just looking at one aspect of thermochemistry, not including our entropy as well as our Gibbs free energy. So as we look at energy in general, it is any sort of potential or capacity, you might say, to move matter. And the movement of matter is anything from literal, being able to see something move, to even just molecules changing. And that's where the kinetic molecular theory is going to play a great role as you think about how the particles are moving, how they're shifting, how the temperature is affecting them. So if you keep that sort of in mind, that's going to help you a little bit with some of our discussion. Conservation, again, both energy as well as matter, really shouldn't be destroyed or created. All right, so that's kind of a typical thing. And then under types of energy, the ones that we're going to be working with are your kinetic energy. So you might remember doing 1/2 times mass times velocity squared is your kinetic energy. And that was a great concept for physics. We're going to be looking at the kinetic energy a little bit more vague. So again, with relation to the kinetic molecular theory, we want to watch how the particles are moving. What kind of motion do they carry? How do they alter as they are changing? Do they have any sort of attractions with each other? So that we're looking at their movement and we're looking at how various factors might affect that movement. With the potential energy, you may have done, mass times gravity times height, and that, again, for physics was great. And you want to be thinking of that potential energy as that space. The whole idea of the mass times gravity times height representing your potential energy is the concept of the height. It's the spacing between your object and the ground that makes a difference. For us in chemistry, we don't want to know how high a particle is from the ground, but we do want to know how far away two particles might be. If they're far away, that dictates one type of potential energy, versus if they're really kind of close together, that's going to dictate a much lower amount of potential energy. So for us, it's still with respect to space, and it's still what's considered our stored energy, but it's going to be between our particles rather than between an object and the ground. And then finally, our internal energy, which we really won't be doing too much with, but that internal energy is supposed to be looking at the particles as a whole. It's taking all of the kinetic energy that you might have. It's taking all the potential energy within those particles. And then it's also including what's inside. What kind of vibrations do those particles have? How is their bond relationship going to be? How do they have transrotational energy? And that as a total tends to be something that you might look at. For our purposes, we are not really going to work too much with the internal energy. We are going to, however, say that if we have a particle at rest, its kinetic energy and its potential energy will be the same. Now, sadly, our particles are really not going to rest. So we're really, again, not going to be using too much with that particular concept. But keep it in mind because it could be useful at a later date. All right. We then have two definitions. So those of you who have gone through physics might remember the calorie and the joule. They're both units of energy. And the calorie is a non-SI unit. So it's a unit that was originally created to represent the amount of energy for water. So it was how much energy was required to change the temperature of a single gram of water by 1 degree Celsius. We do not really use that calorie very much, although you do see the calorie quite a bit in food sources, where a capital calorie actually represents kilocalories. And by food sources, I literally mean that if you were sitting down and looking at a box of cereal and at its nutritional content, you would in fact see capital C calories. So they're talking about how many calories your body is able to obtain from that food. That's really the main area that they now use it. But we're going to be working with the joule, and the joule is an SI unit. It's also part of the metric system, so you could have kilojoules. You could also have millijoules if you so desired. And what we like about joules is that while it is directly related to calories, the unit is actually a derived concept. So it's coming from the idea of kilograms being multiplied by meters squared being divided by seconds squared. And that is really the definition of our kinetic energy, right? Because our mass is in kilograms, our velocity is in meters per second, and then we've squared those meters per second. So it's a much more useful tool as we do some of our calculations. And in addition to that, you do need to know joules are really tiny. A single joule is like snapping your fingers. It is not a lot of energy. So a lot of our reactions are going to be in joules of thousands. You'll see, maybe 40,000 joules are taking place, or 350,000 joules. In a lot of cases, because of that, we're going to convert to kilojoules. But joules is really the unit of interest. All right. As we look at our next section, we have system versus surroundings. And you might remember sort of talking about this when we look at calorimetry, and it is going to be a much larger role in calorimetry. But the system is anything that you find interest in. When you look at the system, with respect to just a simple example, perhaps you are sitting down and you're baking a cake, and I have a tendency to use this example because it's easy. So you've got your oven, and here's the oven door, and in the inside of the oven you can turn on the light and you can see a little cake that's being baked. So your system would be the cake, and your system would be the cake because you're the one who's excited to eat the cake. Because the system is the cake, your interest lies in being able to eat the cake. You're going to pay attention to the heat that's going into it. You're going to pay attention to how the cake is rising. You're going to pay attention to when the cake is done. You're not really paying attention to the other thing, which is the oven, which is your surroundings. Now, the surroundings are technically anything that is not the system. But for ease, what we want to do is we want to look at everything that is at least in close proximity to the system. So the surroundings would technically include the kitchen, it would include your backyard, and that's great, but in order to really make a solid comparison, we're going to be counting just the immediate area to your system as the surroundings that we want to be looking at. So in our example of the cake, we would count that as the oven. So you might pay attention to what the temperature of the oven is as you slide your cake in, But overall, you're not watching the oven. Your interest isn't in the oven and the amount of heat coming out of it, or when does it ignite again, and whether or not the fan is working. Your interest is just not in the oven. Now, in certain cases, your interest may very well be in both, but you always want to define one as your system and one as your surroundings. Since our cake is our system, the heat is going to be coming from the oven into the cake. That then gives us two good definitions. One definition, oh, I thought it was on this page, maybe not. Let's just check here. One definition is endothermic, whether or not you are absorbing energy. And the other definition would be exothermic. Did you in fact release energy? So as we look at our example of the cake is absorbing energy. The oven is releasing energy into the cake. Those two values, if we talk about the magnitude, must be identical. So just to review what a magnitude is, it's just the very simple value. It's the number 2. Whether you're looking at a positive 2 or negative 2, the magnitude is a 2. In every instance of your system and surroundings, your system must be doing one thing with its energy, and whatever that value is, its magnitude must be identical to the magnitude of the surroundings and what it's doing with its energy. Since one of them is going to be absorbed and the other one is going to be released, they will in fact have opposite signs. So when you look at your endo and exothermic reactions, what you're going to see is an endothermic must have a positive sign on it, showing that it is in fact being absorbed, and the exothermic has a negative sign on it, showing that it is being released. If you're instead looking at a reaction, you don't need a sign, because the placement as to whether you put the heat on the side with the reactants or you put the heat on the side with the products, that placement dictates whether it is being absorbed or released. You might have guessed absorbing energy is going to be the endothermic value. So I'm going to write just a capital E to represent the energy. And at the same time, an exothermic reaction is going to release the energy, so it's acting as a product. It's being given out. It's being maybe an explosion even. Somehow you're feeling energy coming from the reaction. Okay, so your system and surroundings, you're going to be paying attention to that. And again, that's going to be a pretty big concept. As we then take a look at some of these other items, you do want to be looking at the definition of heat, and heat is the flow. It's how much heat flows from one area to another. Now, when a heat item is flowing, which is sort of an unusual way of saying it, what you're really looking at is how the particles are changing. And it's the particles changing that actually dictates the flow. So if you had some particles that were moving just really slow, they were kind of clustered together, they didn't have a lot of energy with them, and next to them you had some particles that were just moving really fast. And because they were moving really fast, you could tell that they had a lot of kinetic energy. They had a lot of kinetic energy, and therefore we would say that they had a lot of heat. When the heat flows, it's going to be because two particles from these different areas are going to pass that energy between them. As they pass the energy, the one is going to slow down and the other one is going to speed up. And the idea is that between the two of them, you're going to reach an equilibrium of energy. This is the same reason that you might open the door on a hot day to maybe let some warmth into the room. Or some people might sit down and open the refrigerator on a really hot day and try to get some of the refrigeration air to come back out. The flow that's going to occur is always going to be from the hot to the cold. So anytime you watch this heat flow, you get the particles that are moving really fast, transferring their energy to the particles that are moving slower. And just so that you guys know, it turns out that if you left your refrigerator open, for hours or days even, your refrigerator would never be able to cool down your entire house. It doesn't have that kind of power, which is work efficiency, which you might have learned in physics class as well. The difference between heat and work, on the other hand, is based on what you can get it to do. Work is, the act of doing. It's all kinds of energy. It's lifting, it's, whether it's mechanical energy, whether it's muscular energy, which is really mechanical energy, it's items that fall. So gravity is included in work. Work is everything opposite to heat. So heat is its own category in the area of energy. Work is every other type of energy that might be available. Okay? Within the first law of thermodynamics, what you're looking at is that the entire change, since heat and work are forms of energy, the entire change of energy is whatever you have as your heat, that's the letter Q, added to your work. When you know your amount of heat and you know your amount of work, that gives you the entire amount of energy that is required for a process to occur. So if you have to transfer a lot of heat, you might not get as much work actually in it. If you are getting a ton of work, the hope would be that it didn't cost you too much heat. You might think of it in the sense of like a wheel that has, gears in it. And if the gears have no lubrication, if the gears aren't able to actually rotate, then you end up with no work, but a ton of heat is being released. That's the basic idea. Now, we've already covered the sign conventions of heat, and that's your exo being negative and your endo being positive. We also have a sign convention for work, and that idea is that if you are getting work done by the system, there's that word system again, so the thing of interest, such as a wheel, the work done by the system is going to be a negative value, and the work done on the system is going to be a positive value. Okay. Part 4 of our first law of thermodynamics is the concept that so long as you have a pressure that is not changing, you're going to end up getting a very nice relationship. So the heat aspect that we are looking at is going to be Q. A lot of ours are just not going to give us any work. So the Q value that we're looking at is the Q value of heat. The work value should be how the pressure and volume are changing. And so when we look at heat, this H, that is our enthalpy. As long as we have a nice constant value for our pressure, So we run the reaction in a room where nothing about the pressure is changing. So looking at our cake example, right, we're not compressing the cake, we're not pressurizing the cake. We could, right, we could use a pressure cooker, but we're not looking at that emphasis. Because that is true, the amount of enthalpy is going to end up being identical to the amount of heat energy. So we are literally going to use heat, the word heat, and enthalpy, the process, as identical terms during this entire unit and during most of the next unit when we include some chaos and we include Gibbs free energy. Finally, as we look at heat, again, it's a transfer of energy. And a lot of people kind of think of it as a transfer of temperature, which is a good way of thinking of it, right? Because if your particles are moving fast, it must be a high temperature. If your particles move slowly, it must be a low temperature. So it's a nice temperature. Temperature itself is defined as the amount of kinetic energy that are trapped inside of the particles. So if they are moving quickly, that tells you a temperature, and if they're moving slowly, that tells you a different amount of temperature. Okay, we're going to go over to the next page, and we talked already about enthalpy and endothermic and exothermic. Let's just look quickly at a state function. It is defined in your book, but if we could, let's just take one more look at it. The state function concept is that the route is unimportant to identifying the value. So with a lot of calculations you guys might do, no matter how you go about doing it, it actually makes no difference. So if you think in math, whether you do substitution or you solve a system of equations, if you are looking for an x value and you have all of the same information, the x value is going to end up being the same regardless. That's really what a state function is. When we take heat and we look at whether or not the heat is changing, it doesn't matter if you solve for the heat by doing it in steps. You could solve for the heat by doing it all in one step. You could solve for the heat by analyzing it as, maybe a person is eating the substance and you want to find out how much energy they're getting. It doesn't matter how you do it. The route isn't important. It's the actual answer. And so enthalpy is in fact a state function. We already talked about this, where heat and enthalpy are the same. And again, that's the first law of thermo. Oops. And so I don't think we have too much more to say about that. So what we do want to do is we want to jump down to a very important concept, and that is going to be heats of formation. So this is page 5. And the heat of formation is probably the biggest idea that you're going to have this entire unit. It is the amount of energy to form 1 mole of a substance from its elements at their natural states. So first off, when we're saying their natural states, we do mean their states at room temperature. So if I said oxygen that exists as O2, at room temperature it would be a gas. That would be oxygen's elemental natural state. If I said to you iron, right, that's a solid at room temperature. versus mercury at room temperature is actually a liquid. So you have to be familiar with your diatomic elements, and you also have to be familiar with the phases of your elements. When you're looking at this, the 1 mole is super important. So at the back of your lab manual, there will be an entire data table of thermodynamic data. And that thermodynamic data is referring to a single mole. And you can see that it's referring to a single mole because it's going to be giving you heat energy in kilojoules per mole, meaning that it's over 1 mole. That energy is over 1 mole. When you then use this definition, you're going to take and put the item of interest on your product side. So in our first example, we see we're going to write the formation reaction for calcium nitrate. And calcium nitrate is going to be a solid. In terms of our definition then, we want the amount of energy, so I could look up what this heat of formation is, and I could find it on that table. And we want it to form 1 mole, so that's a product, and we are forming it with an individual coefficient of 1. And we're going to form it from its elements. So individual elements we have here would be calcium, we have nitrogen, and then we also have oxygen. And we want those elements to be at their natural states. So calcium is monoatomic with a solid, nitrogen is diatomic as a gas, and oxygen is diatomic also at a gas. When you follow this definition, you cannot change the number 1. That is part of the definition, that you are forming a single mole of this substance. You can, however, balance your reactants with halves if you need to. So calcium, we have 1 calcium atom present on both sides now. We have nitrogen, we need 2 of them, so we're only going to need 1 molecule of the element. And for oxygen, we have 6 atoms, which means we're only going to need 3 molecules of the oxygen. We didn't need to use any halves in this case, but again, remember, you can if you need to. If you take a look at our next example, we are actually given the heat of formation for water. And we're then given a reaction, and if you notice the reaction, it is the amount of energy. Right, this reaction, we're going to be looking for energy. So we're going to be looking for the amount of energy of this reaction. But notice that we have formed not 1, but 2 pieces of the substance. But we did get it from the elements, and it appears that that's their natural states, right? Oxygen is a gas, and hydrogen is, in fact, also a gas. Knowing that, we can use the information that we're given in this first sentence to kind of make a comparison. That information in the first sentence is saying you would know the formation heat if you looked at the reaction forming 1 mole of water as a gas from its elements, and now they're at their natural states. So the amount of energy for this reaction to occur is negative 241 kilojoules. If we compare this reaction to the one we were given, notice what we have. The one we're given is just double, right? Our coefficients, instead of being 1 and 1/2 and 1, we've got 2 and 1 and 2. Since that's the case, the amount of energy should also be doubled, because we're not looking at kilojoules for a single mole in this reaction. We're actually looking for kilojoules for 2 moles. Let me get rid of the equal signs. We're gonna multiply. And so we'll have negative 482 kilojoules, and that's actually our answer for this reaction. So these heats of formation can tell you a lot of information as long as you know what the entire definition is. And again, this is a good example of a state function because we're clearly not actually creating this given reaction of creating 2 moles of gas. We're solving for that information from a known quantity that came off of a data table of how much energy is for 1 mole of gas of water to be formed. Okay, so there ends this section.